Pete Yost here. Jake and Steve and I just want to thank Huber Engineered Woods for their sponsorship of our Unbuild It podcast. It's easy to speak well of a company when they use building science and systems thinking to develop working systems for high-performance buildings. That certainly goes for the ZIP system. The ZIP system integrates all four control layers: water, air, vapor, and thermal. Its components, polymer bonded coating on OSB, acrylic PSA tape, stretch sill pan flashing, and liquid flash sealant are all top-of-the-line building products, compatible and designed for durability. Throw in the ZIP R panels for continuous exterior insulation, and that's all four control layers. Seem a bit too good to be true? Then consider their system 30-year warranty, their complete online set of info resources, and their top-notch tech hotline. Be the best with the best.
Welcome back to the Unbuild It podcast. I'm Jake Bruton, and today joining me are my good friends Peter Yost and some guy that we met in a parking lot, Steve Basic.
Hi, guys.
And
Hey, Jake.
And today's conversation is a continuation of last week's conversation. Last week's conversation was an introduction to control layers, where we introduced you to the idea of water control, air control, vapor control, and thermal. And then after talking about that, we talked about water. And we talked about things like the red line test. We talked about things like understanding that we want the water to go down, out, and away. And we really talked at length about the idea of continuity. And so I think that that's a great place to start our air barrier conversation, because the same way that we want our water barrier to be continuous, I think that we would like our air barrier to be continuous. And
Jake, before we go any further, I got to say that each of our wives would just be tickled pink to know that the three of us are talking about control and layers.
And I think there are many different layers of control in my house, and I think most of them are my perceived ability of control at home.
The only thing I know about control is forfeit of.
And so when I have a conversation on site with my building professionals, either in-house carpenters, subcontractors, whatever they may be, or for architects, that for that matter, the word continuous, like that's the only word I use is continuous. Does this connect to that? I even had that conversation today with a framer that we'll get into that, I'm sure, today as well. But I wanted to start by saying continuous and then seeing what your reactions were to that word.
Yeah, I mean, I'll start out with that ever-loving myth that we always hear, right? You don't want to build too tight. You want your houses to breathe. Well, that's a load of crap, basically, in my mind.
Also, I'd pair that myth with I've been doing it this way for 40 years.
Yeah, but the problem with pairing that with that I've been doing this for 40 years is that while the logic of, hey, I'm letting my house breathe for the last 40 years, but the construction assemblies have differed. So you're building a tighter building, and I mean, in my personal view, I can't build it tight enough. If I was able to build and design and build a hot air balloon, I would be ecstatic. Because remember what we're talking about here. We're talking about control layers. I need ultimate control to get ultimate performance. So any control I forfeit in view of air leakage, then I forfeit some level of performance. So, when you're talking high performance, control layers, air leakage, it's all simply based on continuity, and the continuity is such that it needs to be, everything at 100%.
And so the easiest way for us to say lack of control when it comes to control layers and specifically air control, we can equate that to leaving a window open, right? If we're letting the outdoor air get inside the house, then it's no different than leaving a window open. Would you agree?
Yeah, absolutely. And it's just a question of how big the window is. The other thing, too, is that, every time you got air moving, you got moisture moving with it. And so the thing that Joe Stieberg and Betsy Pettit drove home over and over again for us was that when you got leaking air, you got moisture moving with it, you have a double penalty. It's the BTUs that you're losing, either losing in the winter or gaining in the summer from air leakage, but then also the moisture that's moving with it. And, it wasn't until the 1980s that we figured out that about 25 to 40% of the total BTUs that are moving through a building are from air leakage. So it's not just a little thing, it's a big thing.
Yeah, and so that continuity certainly plays a role, because I always explain it when I'm lecturing that the moisture can jump on the air train, right? And what I learned from Joe at Building Science was that vapor diffusion really isn't a scary thing. It's when it hits a cold surface, it becomes a scary thing, but you really need to worry about the air train, not vapor diffusion, because you can move a lot more moisture, and I'm sure you can speak to that, Peter, through a leaky hole in the wall than I can through the materials of the wall.
Yeah, for sure, and that's a big leap for a lot of building professionals, is moving the moving that topic from vapor diffusion and how fascinated we get with vapor retarders compared to a focus on air leakage.
I think what I'm hearing from you guys, and I think I'm going to expand upon it, but I think what I'm hearing is the idea of air control also helps to control other layers as well. So if I have no air moving through my wall, I have a lot less vapor moving through my wall. Is that what you're saying, Peter?
Yeah, because if it's air, it's moisture moving as a vapor, and what we worry about is that vapor turning into a liquid. And that's going to happen if we have, warm, moist air moving into the building in the summer, or warm, moist air moving out of the building during the winter.
And we all know what happens when vapor turns into a liquid. It becomes a number one problem, right? It becomes a water management problem
instead of a number 3 problem.
Yeah, yeah.
That's a good way to put it, too. And so what about my insulation package, Peter? Is my insulation package perform better if I don't have air moving through the wall?
Well, yeah, absolutely. I mean, if you've got an air-permeable insulation and air is moving through it, well, the vapor's tagging along, as Steve said, in that train. The other thing that links here is Steve and I spend an awful lot of time making a distinction between a quote-unquote air barrier and a quote-unquote vapor barrier. And these are terms that get used improperly on drawings. And the fact that air moves in very different ways than vapor does. And so it's not just how much water can move with them, it's that the way that we manage an air leak is quite different than the way that we manage vapor moving through a building.
Yeah, and I mean, the other thing, too, that I find a lot out there is the minute you start talking about air barrier, somebody wants to talk immediately about some kind of membrane or, wrap on a house, that they don't understand that, okay, the window and the glass in the window is an air barrier. The sealant around the window is the air barrier. If you're using zip wall on the wall can be your air barrier. The foundation wall is your air barrier, even though some people say concrete can't. To those that say concrete can't be an air barrier, I tell them, okay, let's go on the foundation wall. Put your lips up against the wall and blow hard. I'll go on the other side and see.
See if I can feel it?
Yeah, see if I can feel it, right?
Have you had any takers on that experiment yet?
No, but I have had arguments with, energy raters and stuff saying, oh, you're not allowed to use the slab as an air barrier. And I said, okay, go down there and blow through it then. Let me see you do that. I mean, make a liar out of me. But I've tested houses, with it to extreme numbers of using the slab as an air barrier.
I got to tell you, though, once my wife came down to the basement and I was standing there with a HEPA vacuum cleaner.
Wait, Steve or Peter, this is being recorded. Do you want to tell this story?
I do. I actually do.
Okay.
It's not even PG-13. But she comes down the stairs and I've got this, shop vac and a smoke stick on opposite sides of a concrete block, a CMU. And somebody told me, hey, while concrete is an air barrier, concrete blocks are not. And so I'm trying to pull this smoke through the block with the vacuum cleaner, and my wife just walks by shaking her head like, hey, you don't have a girlfriend and you're not going to bars, so knock yourself out.
I can put up with this level of weird crap going on in my basement.
Exactly. And indeed, I could pull a little bit of that smoke through the block. So, that air barrier tightness requirement is pretty darn tight.
So are you saying that you actually did pull smoke through the block?
Yeah, but there was enough smoke that I was inhaling that the results are a little dubious.
And so, sidebar conversation then as to everything else that we're talking about. Did you try it with more than one type of CMU?
Oh, yeah. So that's really good, Jake, because you are a wingnut, at least in training, if not already certified. The way that we make even concrete and concrete blocks varies from region to region across the country. It's one of the reasons that when we go to test moisture content of things like concrete blocks or concrete, we can't use an absolute scale to get the moisture content by weight. We have to use we have to use a relative scale because the consistency, the matrix of the concrete or the cement block is not consistent enough to develop algorithms for it.
Well, and that's probably true of just regular concrete. I know concrete strength plays a major role in moisture content of the concrete and its ability to move moisture through it, right? So
yeah.
And
okay, so go ahead, Pete.
I was just going to say the last thing is that it's really hard to explain to people that, hey, we're going to build your house tight enough that then you have to have mechanical ventilation. So, the application of building science, while the principles are relatively simple, it does get more complicated if we're looking at not just how the building performs, but how it serves occupants. We should do a separate topic on that at some point.
Yeah, and I mean, it goes back to my analogy of our own bodies, right? I mean, we have a dedicated input for air, and that air goes right to a filtration device. We don't arbitrarily let air get into our system. We bring it in where we need it so we can deal with it. And so the ability, when I speak on this stuff, the ability to gain 100% control means that the air that I do let in the house, then I can treat it and control it, right? I can elevate or lower the temperature. I can elevate or lower the humidity. There's things I can do with that air when it comes in arbitrarily. If I open the window, I don't have that control anymore, right? So you want to close all the windows and you want to gain that control, hence control air, right?
So I like talking to you two about air barriers, air control layers, and I like talking to my carpenters, my in-house guys. But there's two things. I like talking about it from an aspect of I feel like I have a firm grasp on how our building assemblies operate for air barriers. Obviously, we're testing really successful projects for air leakage. But even this conversation and you pretending to say houses need to breathe or I've done it this way for 40 years just irritates the hell out of me, where I just get instantly frustrated from we have one person in our market that owns a blower door that's not me. So I deal with this conversation every time I'm at the lumberyard or every time somebody sees me with a piece of that silly green OSB that's twice as much as regular OSB sitting on my truck. So it's a pet peeve topic and a celebrated topic for me. So it's stressful in some way, I guess is what I'm saying.
And you know what I always find it, this is kind of a little side story to that, but if you just talked about I'm the only one with maybe one other guy that has a blower door in your market. So if you're in a lumber yard and there's the 6 builders that don't have a blower door, I sit there and say, what a great opportunity for you to set yourself apart and make yourself, seem like there's more value. Even if there isn't more value, you can give the appearance of more value because you got a cooler tool than the other guys do and you know how to use it. And it's like, hey, I'm going to come in before I remodel your house. Let's do a blower door so when I'm done, we can do another one and we can measure the difference. I mean, what a novel idea that is, huh? Getting a little knowledge. It's crazy.
And translating that into, comfort and indoor air quality for the customer. I mean, I hear that all the time. Oh, yeah, Yost, you work on high-performance buildings, but, yeah, they're more expensive. And, that is such a red herring. I know that cost is important, but people buy expensive items based on way more than first cost. And if you tell somebody that you can give them greater thermal comfort, and better indoor air quality for their kids, that's going to be a huge advantage, because so often we do have problems with thermal comfort and indoor air quality in buildings that aren't airtight.
And I would
Peter,
say that that's the biggest hurdle for selling the high performance aspects of our company, is getting people to understand the benefit.
Yeah, and it goes back. I mean, Nathan had one of the best analogies there, talking
Nathan
about
who?
risk. Nathan Yost, Peter's brother, when we worked with him at Building Science. And Nathan would always talk about how close do you want to build to the edge of the cliff, right? And you could have 10 builders that, one has really good knowledge and the other 9 have mediocre knowledge, and they're going to roll the dice in the hope that what they build will make it. And out of those 9, probably 7 will make it, and it won't be a problem, and they'll continue business as usual and say, hey, it works for me. You don't need to do all that crazy stuff. But then there are those 2 that are going to get caught, and they're going to fall off the cliff, or it's going to collapse underneath them, and that's the end of them, right? Because they didn't take the time to understand it, and they didn't take the time to understand what risk was involved and how to mitigate that risk.
Hey, so we talked about how important controlling bulk water is, and then we moved on to air. And then the third one is going to be vapor management. And I just want to start the transition from air to vapor to say that the amount of moisture you can move through air leakage is about 100 times greater than you generally get with vapor. Now, there are some exceptions. If you're doing indoor swimming pools, or if you're doing an attached greenhouse of 1,000 plants, yeah, that's a level of vapor pressure you're going to have to deal with. But
that's a different model.
For most buildings, the number of times they're going to get into serious trouble from just vapor by diffusion alone is, 1 in 1,000 compared to the buildings that get into trouble because of air leakage.
Right, and I would bet that those couple builders that do get into trouble, they don't know that they're in trouble because the wall is, there's stuff growing on the inside of the wall, and they just simply don't know about it because nobody's gone in there to check, and they haven't had a major failure at the moment. But that doesn't mean it was the right way to do it.
So then, to continue the conversation into the vapor realm, I think it's best to start the conversation with a question. Cool. Do I need a vapor barrier?
I'll go first.
Go ahead.
So, I think this is the best example of where there's a difference between barrier and control, because vapor is more about managing than it is, sort of continuous linking of various parts of the dedicated layer. And to me, the most fascinating thing is once a building gets wet, the only way to dry it is by diffusion. So for me, that vapor control layer is way more about, can I get the building to dry if it gets wet, rather than is the building going to get wet by vapor?
How do I stop it?
Yeah, and the whole reason we developed vapor retarders was because of wood frame buildings getting wet in the 40s in a northern climate. And from that, we spread the logic of a vapor retarder through all kinds of buildings, not just wood framed, and through all kinds of climates, not just cold
And with
climates.
that, Peter, let me ask you a question to get your opinion, because I think I've asked this before, but I'm going to ask it for the benefit of our listeners here. In those 40s or in those years, 50s, when people built houses, we know that a lot of people
When
used
Peter was
poly,
building houses.
Right. We know people that use poly and stuff on the walls. My argument and contention is that the poly really acted as a very bad air barrier and not necessarily a vapor barrier. So while moisture can't pass through it, the saving grace of having that piece of poly there was that a lot of air wasn't moving through it, so there wasn't a lot of moisture on that air train moving through it. So it wasn't that the poly was a really great vapor barrier, but it was more of it kind of saved your butt by being a really poor air barrier.
And maybe it was doing double duty.
Yeah, I mean, that's how I have always kind of looked at the vapor barrier systems.
Yeah, well, I think it's a little trickier than that in that air leakage is about highways. It's about two holes connected by a driving force, whereas vapor pressure is a field effect that's exerting equal pressure across the whole wall. And this is why when Joe would give the example, like if I have a piece of plastic and I poke enough holes in it that represents 10% void, do I have a 90% effective vapor retarder? And the answer is yes, because the vapor pressure is pushing equally across the whole field, and the molecules can't talk to each other and say, hey, there's a hole over here, let's all run through it. They're all pushing the exact same force wherever they're located. That's not true for air leakage. Air leakage is that there's a highway, and they do say to each other, hey, look, there's a highway here, let's run through it.
Well, it's kind of like if you think of those two as loads to a building, then you're saying vapor is a uniformed load, and air leakage is really a point load.
Oh, I've never heard it expressed that way, but that's exactly an analogy. Yeah.
You're welcome. I told him that 3 hours ago.
Oh, cool. Would you have admitted, Steve, that was actually
Hell
Jake's?
No, he didn't say that. Do you know what a uniform load is, Jake?
Now that I've heard you reiterate it to Pete, I think
no,
I have
a uniform load is when you've got a really heavy coat as part of your uniform.
There you go.
Right?
Yeah, or a backpack.
Yeah. Sorry, Pete, that wasn't funny.
And think about it. That vapor retarder
That's what makes it funny.
That vapor retarder layer is just about managing winter movement of warm, moist air into the assembly. The rest of the time, it's blocking drying to the interior.
What if I live in Houston?
Just as a side note, just so you guys know, one of my goals in conversation with Peter is to see if I can get him to stall and totally forget what he's talking about. I consider that a personal success when I can do that. So
it's not an easy task either.
No, not at all.
Thanks so much for sharing, Steve. Now I can't remember what I was going to say.
So my question to you, Peter, is you said you were talking about cold climate and it keeping things from that warm, moist air from getting into the wall. Well, what if I live in Houston? Isn't there a need for vapor to slow down vapor drive in Houston or Miami?
Yeah, so that's a great question because you could end up with vapor pressure from the outside to the inside of the building in Miami that's actually a greater vapor pressure than what we get in a cold climate from during the winter. What we really want to avoid is that first condensing surface, right? Because what we worry about is when it changes from a vapor to a liquid. So a perfect example of that is, if you switch to vinyl wallpaper in Houston, and in the summer you've got warm, moist air, pushing from the outside environment in, if that first condensing surface of the backside of the gypsum board is really, really cold because of the air conditioning inside the building and there's a vinyl wallpaper on it, now we've got exactly what happens in the winter for first condensing surface happening in the summer in warm, hot, warm, moist climates.
Every time somebody says vinyl wallpaper, I think of, me, Neil Moyer, and Joe down in Florida in a hotel that someone just slept in the room. We're doing a building investigation. We peel off the vinyl wallpaper, and it is literally a mold mosaic on the wall. It was absolutely frightening that somebody was sleeping in that room the night before. Crazy.
Yeah, and part of that is that, if you were to pick a medium to grow mold, a gypsum core with a thin layer of paper on it, that's a pretty good choice for setting up.
Something that holds
it's like a
moisture
chia
with
pet.
a little bit
It's
of edible.
Yeah,
It's
exactly.
a home building chia pet, Peter. You spray it with water and just kind of watch it grow.
Yeah,
Give
yeah.
it a little heat.
But
Okay,
the other
so
thing
that's
about
a good...
the other thing about vapor too to be concerned about is when you get into specialty areas, right, in climates too. Like I've done natatoriums and personal indoor pool buildings or wine cellars in the basement that are under heavy controlled environments that have a relatively high humidity that you don't want it to get into the rest of the house. So it's not necessarily even about the building in general. It could be a compartment within the house that can't really communicate with the rest of the house for that reason of a high vapor pressure.
And what's interesting about that, Steve, is you and I have both worked on a couple of projects and shared about, natatoriums, indoor swimming pools. And, the 2 times I've been involved in it recently, the key thing was, if you're not going to do a perfect air control layer, don't even worry about, what sort of vapor retarder you have to have, because that will overwhelm your system. Yes, I want you to worry about the vapor retarder and whether it's class 1, 2, or 3. But before you even go there, you better make sure you have a really, really good air control layer, or it'll all be for naught.
Yeah.
When we talk about the indoor swimming pool and the greenhouse, when I was at summer camp 2 years ago, somebody at summer camp, building science summer camp, was telling me that the bulk of their business was consulting on grow rooms in Colorado for marijuana dispensaries, because they were dealing with enormous spaces that they have to control everything inside of, including humidity, and then they have to have durable assemblies that'll still last. So it was a really interesting conversation where it's just like, oh yeah, that's a wine cellar basically. You're controlling everything inside the room, or it's a swimming pool. It's just different levels of different things. And whenever I hear swimming pool, I immediately go to that conversation and think, oh yeah, a bunch of people grow marijuana in Colorado too.
And getting back to your original question, Jake, of do we need vapor barriers and what is our opinion? Now that we got through Peter's opinion, I'll share mine.
Can't wait.
The first question I always ask when people say, what do I need a vapor barrier? I said, okay, well, where's the moisture coming from, right? Because to have a problem, I need a source to create the problem. And I tell people, me personally, if I build a relatively airtight structure, then the vapor problem really doesn't become a problem as long as I pay attention to the surface of that first condensing surface, the temperature of it, right? If I can lock in those 2 things, control the airstream and control the first condensing surface, then I don't feel like there's this major problem.
Okay, so controlling that condensing surface then brings us into our discussion about thermal, correct?
Oh,
so
nice
if we're
one, Jay.
able to, thank you. We're able to talk about putting a sweater on the outside of the house then.
So I think, Peter, give us the quick building science 101 on insulation. Talk to me, buddy. Talk to me, Goose.
Yeah, so step number 1, we put insulation in cavities because they're there. So that's the first kind of thing we have to deal with, which is, yes, we can talk about exterior continuous insulation and its benefits, but we mainly put the bulk of our R value into framing cavities in walls and roofs because we have that space. We've sort of already paid for it, and now we want to use it. It is not the best place to introduce insulation. In fact, it's pretty easy to look up Joe Stiebrick's perfect wall, and the perfect wall is one in which we make sure that we have all of the insulation on the outside of the cavity. So the cavity is seeing conditions pretty similar to what we're seeing inside the building. The framed wall likes to see the same conditions we do, and the way to make sure that happens is not to put any insulation in it at all. That's not very realistic. We need to use that space. So now what we're going to do is put enough insulation on the outside of the cavity, on the outside of the building, so that we warm the cavity enough to avoid condensation in that cavity. And that's going to vary by climate. It's also pretty cold climate centric, right? Which is a pretty significant bias in our industry, in that a lot of the building science is a bit more tuned or defaults to cold climates than it does warm climates or cooling climates.
Because in reality, we almost all live in houses that we're paying to condition on the inside. Because we're all trying to control that temperature inside, and one of the things to do that is the thermal barrier. Why would we, the temperature difference between 120 degrees outside in West Texas and 68 degrees inside is not that different from 68 down to 0. It's still just trying to keep inside air inside and conditioned, and keep the outside air outside.
Yeah, I dumb it down even further. When people say, do I need insulation, or do I need a lot of insulation here? My answer to that is actually a question. Do you buy energy to condition your house? Because if you buy energy to condition your house, then the thermal barrier or thermal control layer is developed there to take that energy that you're purchasing and hold on to it as long as you possibly can. And that's whether it's cooling energy or heating energy. It's energy. You've paid to convert that energy somehow, some way, in your boiler or air conditioner or heat pump, whatever it is. You purchased it. Refrigerator. So why not hold on to it as long as you possibly can? Right.
And the other big benefit of having the insulation on the outside of the building, as opposed to in the cavity, is we can make it continuous, right? So that means that we get a more even bang for the buck for the per thickness of the insulation on the outside of the building.
And Peter, I'm going to piggyback your story, because as a young architect at Building Science Corporation, I get to sit down one day at lunch with one of the greatest minds of building science, one of Joe's mentors. And, as a young architect, I didn't know the answers, but I had a feeling on some of the questions, right? And I asked him, I said, hey, what's the best wall that I can build? Like, give me some secrets here. Give me the secret sauce to building a wall system. He simply said, put as much insulation on the outside of the wall as you can afford, and you'll never go wrong.
Yeah.
Which comes back to that condensing surface again.
Yeah. And not only that, but think about when you put that rigid layer of foam on the outside of the wall, and I'm going to use, the R panel, because I've used it as on a lot of projects, Zip R panel, and, you can get in 3, 6, R9, R12. We commonly use the 6 and R9 panel a lot. But if I take a 2x4 wall, and I put an R15 bat in it, well, the cavity is R15, but at the stud, it's, R5. Something like that. And then the windows are R3. So when you go through the whole wall R value, you end up with a number. And these are kind of fresh in my mind, because listen to JLC, or pick up the JLC here next month. I wrote an article on this very subject. And but the minute I put rigid insulation on the outside to the tune of R6, while in the cavity at R15, that goes to R21, the real important thing is at the stud that was R5 now goes to R11. So I've doubled the thermal control at the opaque surface in a wall system, which, if you're a good framer practicing advanced framing, that maybe accounts for about 15% of the wall. If you're a framer where, you can't put enough wood in the wall, that might account for 25% of the wall. But it's a huge help, because it's literally putting that blanket or sweater or whatever analogy on the outside. And, I tell those in cold climates or any climate, as a matter of fact, if you don't think rigid insulation in a continuous fashion and continuity is that important, then the next time you lay down on your couch to watch a movie on a Friday night, and take your wife's blanket, cut it into 16-inch strips, and then space them over her with a couple, 2-inch spaces in between those strips, and see how long, your comfort lasts.
The analogy works, but don't go cutting up a blanket and blame Steve. That's for sure.
Yeah, the other thing that I'm going to steal a little bit of Steve's thunder here is, because I love this part of the way that you think about thermal insulation, Steve, is that the other control layers, water, air, vapor, we want those continuous, and we want them as continuous as we possibly can. With a thermal layer, it's proportional to what the delta T or the temperature difference is, or the amount of energy you want to save. So it's the only one, in my opinion, where you pick a level that you can afford, but there's no like
scale.
Absolute minimum or maximum. It's a matter of choice based upon how much you're paying for energy and how much money you can spend on it.
But I think that's a choice that transcends, laterally through every design performance choice of a house, right? A house that I build in San Diego, which is virtually, I can open the door, go outside, inside, and it's the same environment 90% of the year. That's different than building a house in Minneapolis, because when I walk outside in February, it's not the same that it is inside. So there are proportional decisions that have to be made there. And, we'll get into this. I think, maybe one of these times a good podcast would be proportional decision making, because it doesn't make sense to, like you said, to put R9 on a wall, on a 2x8 wall, fill up the cavity, and then put an R3 window in the wall, right? It doesn't make sense. And it doesn't make sense to necessarily put an R9 2x8 wall in San Diego. So...
Well, and actually that conversation about windows and glazing is part of the insulation conversation as well. When we think about it, we have a tendency to talk about R value of the fluffy stuff that we're putting in the wall and forget that we also need to be talking about the U factor or the R value of the glass, the glazing, or the unit as a whole as well.
Well, strike one up for you, Jake, because I think it's not even just windows. I think when you look at every material almost plays a role in what part of the water management system is my sheathing? What part or role does it play in my air leakage continuity? What role does my sheathing play in my vapor transmission? And more importantly, as Peter pointed out, my wall's ability to dry. I totally agree with that. That's probably one of the most important parts of vapor diffusion and vapor management is I really don't care so much how much vapor gets in my wall. It's how much vapor can I get out of my wall if I have a problem. And the same with thermal. It's, a window is a piece of insulation. It's a rather poor one, but the wood frame is a piece of insulation. The glass panes or IGU is a insulation, and it's a vapor retarder, and it's an air barrier. And oh, by the way, it's a water management layer. So it's how we put all of this stuff together. And I mean, someone should really come out with a podcast and find a way to break down all these components in a real intelligent way and speak to an extremely intelligent industry and provide some direction in this arena. I mean, I don't know what you guys think, but I think that would be a really great idea.
The master unbuilder has spoken. Hey,
I like the idea of a continuing game where we name a building component and say, is it an air barrier? Is it a water barrier?
I got a quick wrap up for you here too. Is it more important in what plane you locate your water control layer, or that it's continuous?
So for me personally, when I design, the least amount of coastlining I can do with the water management layer, the more confident I'm in it with it. Meaning, so the most confident water control layer is, right, if I put a piece of zip sheathing on the wall, tape it. I'm pretty confident in that. If I poke a hole in the window and I keep the window in the same plane as the zip sheathing, I'm pretty confident in that. Move that window in 6 inches, now I have this lateral displacement where I introduce horizontal or very minimally sloped surfaces where
Little bitty roofs.
I have problems. Right.
But you'd rather have it continuous than be forced into locating that water management layer in one particular plane or the other.
Yes.
Okay. And what about the air control layer? Is it more important that it's continuous, or more important that you locate it on the outside of the wall, the inside of the wall?
I'm going to make
an
an argument that continuous is the only thing that's going to matter for me for air barrier. Obviously, the least amount of moving things around and connecting dissimilar materials is better, but continuous is the only thing that matters, because if we're not continuous, then it doesn't matter that we did it short or only on the outside.
That's exactly what I was driving.
I'm totally on board with that, and I would preach that to my death. That I don't care what material you use and where it's located. You need to understand the intent of what you're doing. And we get those, Peter, we get those questions all the time. Well, where's the best place to put the air barrier, on the outside or the inside? And I know there's a lot of people that, they'll put Intello on the inside of the wall and then a service cavity and all this stuff. And yeah, that works. And it works really well if you understand the intent of what you're doing. But I think you can come up with other solutions that you can understand the intent of what you're doing that work just as well.
Might be less complicated too.
Yeah.
Excelente.
And
so I think that's a...
Well, I was just going to say, the other part too is, that I think is really important. Control layers don't have a financial boundary, right? So what I'm trying to say is, if you're in the business of, say, buying lots and doing affordable housing in Houston, control layers still matter just as much as if you're doing a $3 million house outside of Boston, right? Now, the materials might be slightly different, the windows might be slightly different, but the concepts are the same. Like you can't value engineer out control layers or value engineer out continuity, because you're just going to put yourself at a higher risk. And here's the kicker. When you start doing that with lesser materials, then I'm challenging the house in two ways, right? I'm putting a lesser value product in, and I'm installing it in a lesser value installation. So it's kind of a, I'm shooting myself in the foot twice there by doing that.
Excellent. And not only that, Steve, but, most of the work that all three of us do, when we talk about high performance, it's dealing with these four control layers. Like, it's not an option for us. It's something that's part of making a durable, healthy building for any occupant, wealthy or affordable.
Yeah.
Yeah. Like we say, Peter, it's not rocket science, it's building science, right?
Right.
Yep. I'm building a 1,200 square foot house that's going to be a rental for the clients. And all of these things are at the forefront of our discussion before we move on to countertops.
Yeah. Excellent.
So, okay, that's a good point for us to wrap it. This was Season 1, Episode 4 of the Unbuild It podcast. We thank you for tuning in. Until next time, I'm Jake Bruton, joined by Steve Basic and Peter Yost. Say goodbye, guys.
Goodbye, guys.
Goodbye, guys.